Yeah, thank you very much for inviting me. I'm really excited to be here. And yes, most of my talk will be about duality, but I figured is this working? I figured I cannot not have a couple of slides on IV, which is kind of how I started working with Ken. So the kind of motivation behind IV, or at least as I see it, is that SMT-based verification with rich theories and quantifiers really goes a long way and lets you verify very interesting systems, but the user experience is kind of problematic, and a major pain point is instability and opaque failures, because you mix quantifiers with rich theories, or you can encode things pretty naturally, but then when the solvers fail, you're kind of left with very little insight into what to do. And kind of the idea with Ivy, which really came from Ken, is to make us work a little harder to model the system in a decidable logic, and it could be EPR or a few other logics. And then we get much better automation. We get stability, and we get counterexamples, and we get transparency from failures. And this really went a long way. So this picture here is from a presentation we both gave at Symposium on Static Analysis in 2018. And I think the conclusion slide from that talk kind of still applies, that we use decidability in order to get productivity. And it's kind of a way to get better productive use of automated theorem provers like C3. And for decidability, of course, encodings matter. And we have, over the years, we've had encodings of many interesting distributed systems and also liveness properties. So I guess a few things changed since this slide. The open source repository is not hosted under Microsoft anymore. And we have a tool paper that you can look at if you're interested. And it really led to a lot of works on Paxos and other interesting distributed systems, proofs of liveness, more kind of interesting protocols, and also testing of protocols. And most related to what I'm going to talk about for the rest of the talk is that it kind of opened the path to a lot of works, both by Ken and I, and also by others who are not affiliated with us, to try to take these protocols that were modeled in a way such that checking their environments is decidable, and try to find these environments automatically, now that environment checking is reliable. And I guess it's really been a great journey, Ken. It started for me, at least, in my in a visit to Microsoft for a week in 2014, and then an internship in 2015. And I remember, so when Muli, my advisor, Muli Sagiv, was also visiting Microsoft, and Muli and I were at Microsoft. And I remember I was like a year into my PhD. I already had one Popper paper and another Popper paper that I just submitted before coming to the internship, and I was feeling like pretty competent as a PhD student. And then I met Ken, and I remember a few weeks after into the internship, I told Muli, look, I'm not sure what I can do. This guy Ken, he's thinking better than me, he's proving the theorems better than me, he's hacking the code better than me. What can I contribute? So the way it went in the internship is that I'm not sure, I think somewhere along in the middle of Muli went away for a week. He was some conference in Europe, and Muli went. And then I had some time to myself, and I said, okay, I have to do something to justify what Microsoft is paying me here. And then I did something, and I hope your experience of my competence was better than mine. But anyway, it led to a lot of follow-up research and the continuous collaboration, and I'm very happy that this is how my kind of PhD experience started. All right, so this is all I'm going to tell you about Ivy. This has been going on for a long time, and I want to tell you about some more recent things that I'm doing that are also heavily impacted by things I learned from Ken. And this is this notion of duality. And what I'm trying to explore here is that many algorithms in verification have kind of a primal dual search feeling where there is a duality between proofs and counterexamples. And the classic duality in computer science of this flavor is linear programming, but we also have it informally and in many verification algorithms. And of course, Ken has a tool called Duality from 2003. And it also kind of expressed this observation that there is a useful duality between models and proofs. And many of these tools kind of simultaneously search for a proof and a counterexample, and these two searches guide each other. And the motivation for this line of research is that hoping that more rigorous understanding of this could be useful, and maybe it would be. So I want to talk about two contributions that came from kind of this line of research. One is induction duality, which I'll talk about more briefly, and then I'll go into more detail on this new Lagrangian one. All right, so this induction duality is a paper that appeared in PubMed 2022, and Ken is a co-author, and this paper also has a kind of an interesting anecdote to it, that I think it was submitted a total of 5 times before it was accepted. One time we withdrew it after the submission, and the rest it was rejected. And I was pretty frustrated with it. And I remember
it doesn't count as a rejection if you withdraw it.
What?
You withdraw it, doesn't count as a rejection.
Yeah. But I remember Ken telling me, look, Oded, sometimes the thinner the contribution, the easier it is for a paper to get accepted. And I think this is some. I'm hoping that this is what happened with this paper. And actually, at the end, we did kind of cut out a few things and made the contribution a bit thinner, and I think it helped the paper get in. But it helped me at the time that that Ken encouraged and supported me, so I'm grateful for that. All right, so let me tell you a little bit about what is this induction duality. So it's a formal symmetric and kind of surprisingly symmetric connection between execution traces and a certain form of incremental induction proofs. And it led to this new Primal-Dual algorithm that we call Primal-Dual Houdini, which we get kind of by taking the classic Houdini algorithm, just a fixed point computation in a predicate abstraction or Cartesian abstraction. And if we reflect it across this duality, we get kind of a weird thing that we call dual Houdini. And it turns out that when you combine them, you can get a Primal-Dual search algorithm for infinite inference that's kind of symmetric between proofs and counterexamples. So I'll share with you a little bit about that, and then we'll move on to the Lagrangian duality. All right. So let's spend some time with this kind of interesting program that's manipulating 3 integer variables, and you see that they're being updated here simultaneously. And we want to prove that A is non-negative. Now, a very common way to think about this program as a transition system or as a graph, where you start at an initial state and then you have transitions, and they lead you to reachable states of the programs, and the values here are the values of A, B, and C. And of course, you also have edges in this graph that are between unreachable states. And these edges do have a meaning. For example, if you would, for some reason, believe this state to be reachable, then you should also believe this state to be reachable. And of course, the classic way to prove this program is with an inductive invariant. And for this program, this assertion is not inductive just by itself. We need to strengthen it a little bit. So we need to also say that B and C are non-negative. But we can also prove it a little bit differently. We can prove it with incremental induction. And this is kind of a classic idea, goes at least back to Mann and Knueli. But what's a little less classic is that I'm depicting this process here as a graph. And this process is where we start from true. We don't know anything about the program. And just by induction, the claim that C is non-negative is inductive because of the way C gets updated. And once we know that, we can prove by induction that B is non-negative. And once we know that, we can prove that A is non-negative. And we can put this in a graph. And this graph starts at true, and everything that you can reach from true is an invariant of this program. But kind of similar to how this graph has edges between unreachable states, this graph might have edges between predicates that are not invariants of the program. For example, if for some reason you believed b equals 0 to be an invariant of this program, then by induction it follows from how a is updated that a equals 0 is also an invariant of this program. And kind of the intuition of this graph is that edges here are an implication. You have an edge from P to Q. If by application of induction, it follows that if P is an invariant, then Q is also an invariant. And let's try to formalize this. So this is the formal connection that if you start, or if you like it better, you can look at it like this. If you start at a state that satisfies both P and Q, and you make a transition to a state that satisfies P, then that state satisfies Q. I think the best way to look at this is visually. So if you would have an induction step from P to Q, if for every transition from S to T, if S satisfies both P and Q and T satisfies P, then T should satisfy Q, or you cannot have a situation like this. And you can kind of contrast this with the relative inductiveness notion of IC3. It's very similar, except that we're not assuming P in the post-state there. And kind of what's striking about this visualization is that it's completely symmetric. So if you think of this as a connection between two graphs, you can just swap the roles of the two graphs and it's the same. And of course, this relationship kind of lifts to paths in the graph. So if you have a path in this graph and a path in this graph, and you start from a point here that's related to all the points here, let's say all the points here are satisfied by predicates that are satisfied by initial states, and let's say you start from true here, so it's related to everything, then every point here is related to every point here. So any reachable state satisfies any invariant, which is a reachable point in this graph. Yeah, the proof is kind of very easy. If you just take a minimal violation, you get a contradiction. And it's kind of a striking symmetry between proofs and counterexamples, or proofs and executions, where we started out by thinking of these paths in this graph as incremental proofs about reachable states of this graph, but you can also take the other perspective, that paths here are incremental proofs about things that are reachable here. It's kind of confusing, I guess. And you can kind of contrast it maybe to the famous slide from Andreas' talk this morning, that a program, but really what he meant was the kind of the error traces should be covered by the proof. It's a very asymmetric connection, but here it looks like that you can put them on an equal footing. So I think it's very interesting. I won't say much more about this. Oh yeah, I guess I will say one thing. So yeah, I said a couple more things. So we kind of the fact that things are so symmetric mean that you can actually take an algorithm and just take its dual. And if you know the Houdini algorithm, as it runs, it kind of generates counterexamples to induction, and dual Houdini kind of generates dual CTIs, which are induction edges in this graph. And then our idea was to kind of connect the states that you get from counterexamples here as the input to dual Houdini. So Houdini takes an input, a set of predicates, dual Houdini takes as input a set of states, and it generates kind of as a byproduct some predicates, and you can feed those into dual Houdini, and you get a Primal-Dual algorithm that can find inactive invariants or counterexamples. It has many interesting and nice theoretical properties. It has the proofs of these properties kind of highlight the duality. I really like it. I encourage you to look at the paper. And I'm putting here this figure because it's kind of a very nice illustration of this new induction duality versus the Galois connection. These are two figures. Here it's the lattice of sets of predicates, and here sets of states. And you can kind of illustrate the operation of Houdini on each of them, or Houdini and dual Houdini. And if you take the vertical flip between these two sides, it represents the Galois connection. And if you take the horizontal flip, it represents induction duality. So this is all basically just trying to tease you to read the paper. But I can also share another anecdote about Ken, that, you know, I was so thrilled with the beauty of all of this. But whenever I would talk to Ken, it's a hard sell for trying to sell you something. you always ask me, okay, so beautiful, but what is the heuristic value on the examples? What is the heuristic value that this approach gives you? And I think it's I appreciate that a lot. It's kind of also grounding me to the empirical reality and the importance of actually evaluating this on practice on our interesting examples. But just out of spite, I won't show you the empirical results right now, but they were pretty good at the time. All right.
So can you briefly tell us, is it like, does it let you, just answer this, does it let you prove more things, or does it let you prove the same things but much faster?
So at the time it was published, it also let us automatically find more invariants that other techniques couldn't. Now there are other techniques based also on IC3 and other techniques that kind of comparable. But I think this idea is still, there is still a lot of potential. I think we applied it for distributed protocols kind of modeled in the IV way, but there is room to apply to many other domains, and I'd be very happy to talk to anyone who's interested in looking at that together.
So, but
Yeah.
maybe a related question. There's a theory question this time. So is there a class of invariants that are more amenable to this method than other types?
Yes, absolutely.
Okay.
It kind of depends on the fact that you can incrementally build them. It's related to acyclicity of some dependency graph. Yeah.
Nice to know. Okay.
Yeah. All right. So now let me talk about this kind of Lagrangian duality, which came out of the question of can we kind of generalize this? So in Primal-Dual Houdini, the duality is very formal, very symmetric. But what about all these other algorithms that we kind of feel that they are Primal-Dual? Can we make a formal sense of that? The answer is that yes, and this is a recent Popple paper with also Takeshi Tsukada, Hiroshi Uno, and Sharon Chohan. It's presenting a framework that is inspired by linear programming, and it is actually able to capture many existing verification algorithms. It kind of lets us draw interesting comparisons between these algorithms, and the paper also contains a new algorithm for fixed point logic that was kind of inspired by these insights. But I focus on the framework and the insights.
What is quantified fixed point logic?
It's a logic that has both quantifiers and the fixed point algorithm.
It's called fixed point logic.
Okay. I will know what quantified.
You say quantified first order logic.
Yes,
You do.
maybe I should stop. Yeah. All right. So kind of the inspiration for this is the Lagrangian that people write in linear optimization, which comes from trying to optimize a function under constraints. I won't get that much into it, but it's just a function of two arguments. And if you take the sup inf or you take the inf sup, turns out the result is the same. That is called strong duality, and it's over real domains in linear optimization. And the way we generalize it is we let x and y just be arbitrary sets, and z be a totally ordered set. And you'll see that usually it's going to suffice for us to be -1 and 1. And if the sup inf is equal to the inf sup, this is what's called strong duality. This doesn't always hold, but the fact that the sup inf is less than or equal to inf sup, this does always hold. It's the same as having the implication between exists for all and for all exists. Here's how we kind of applied for verification. We typically let this x be the set of possible, maybe partial counterexamples, partial or abstract, and let y be the set of possible or maybe partial proofs. And then we define the Lagrangian to be -1 if x is a counterexample that shows why the proof in y is not good, and otherwise it's 1. And then you can think that you can think of it as a two-player game. We have one player that's kind of trying to find a proof and one player that's trying to find a counterexample. And then we kind of write a very simple abstract procedure. So you start at some arbitrary point, and suppose that this is the Lagrangian, that here it's 1 and here it's -1. And you ask, can the x player minimize the Lagrangian? Can he change it to be -1? And from this point, yes, the x player can go here, so you go here. And then you ask, can the y player make the Lagrangian 1? And in this case, it can, so you go here. and then you let the X player take another turn, and then the Y player take another turn. But now the X player cannot make any move that would make the Lagrangian -1. So you declare victory and you say that you have a dual solution at this place. If things were different, you might have had a primal solution. All right, what if the Lagrangian looks like this? Well, in this case, you might start here and then let the X player make a move and then minimize the Lagrangian, and then the Y player could maximize the Lagrangian by going here, and the X player could go here, and then you can get into this infinite cycle. So there is kind of something that we need to introduce, which is monotonicity in order to make progress. So if either X or Y have a lattice structure and the Lagrangian is either monotone on Y or anti-monotone on X, then we can actually ensure progress if we monotonically update. So instead of just updating to the new point, we take the join with the prior value. And this is basically our abstract algorithm. It's kind of very straightforward. And it gives us some theoretical properties like partial correctness and progress. And if you also stratify the one of these sets, you get termination guaranteed. And what's really cool about this very simple algorithm and this Lagrangian framework is that it can actually describe many existing algorithms in verification. I'll give you a couple of examples. The CIGAR algorithm, counter-example guided abstraction refinement. So the way we describe it with the Lagrangian, skipping a little bit. So I bet most of you know it, but I'll just give a brief description of CIGAR. So if we have some finite set of predicates, we can partition the state space into a finite set of equivalence classes just based on the evaluation of these predicates. And then we can define an abstract transition system that just operates over these equivalence classes. And if it's safe, then the original system is also safe. But if it's not safe, we either found a real counterexample, or maybe we refine our abstraction based on the abstract counterexample we found. So what an abstract counterexample looks like is a sequence of transitions, but they don't exactly connect. These transitions end at the state S1, and this one starts at S2, and they're equivalent up to this abstraction. They agree on all the predicates in A, but they might not be exactly the same state. And the way we find the abstraction, we add at least one predicate that kind of breaks the equivalence at some point along this abstract trace. So let's write a Lagrangian for this algorithm. So we make the X be sequences of states that correspond to these sequences in the abstract counterexample, and we let Y be finite sets of predicates ordered by inclusion. And then the Lagrangian is going to be -1 if this sequence is an abstract counterexample trace to this abstraction, if it has this form, and otherwise it's 1. And now if you think about what this kind of two-player game algorithm does, is you start at some arbitrary point. Maybe you start it at the empty trace and I don't know, just the safety property or something like that. And then you let the X player try to take a move to minimize the Lagrangian. And the way X would minimize the Lagrangian is by finding an abstract counterexample. And then you ask the Y player, can you make the Lagrangian 1? And the way the Y player can do that is by adding predicates that would refine the abstraction. And in this case, we would monotonically update Y. We would just accumulate predicates. And then the X player takes another turn and the Y player. So this is the CIGAR algorithm. All right, another classic algorithm is the ICE learning algorithm, where if we have a set of positive states, negative states, and transitions, we kind of ask ourselves, can we find a predicate that's an inductive invariant just for the system restricted to this finite set of positive, negative, and transitions, or positive constraints, negative constraints, and implication constraints. And then we check, is this an inductive invariant for the whole system? And if we get a counterexample, we add it to our finite set, and then we try to learn a new predicate. So you can also find a Lagrangian, define a Lagrangian for this algorithm. You let X be these finite sets of positive, negative, and transitions ordered by inclusion. And you let Y be just a space of predicates. And then the Lagrangian is 1 if the predicate is an inductive invariant only for these examples, and -1 otherwise. And again, now if you instantiate this algorithm, this time monotonically update X, you exactly get the Seeger algorithm that the X player will try to check if it's an inductive invariant, and if not, it will add an example that shows that it's not an inductive invariant, and then the Y player will be forced to find the predicate that is an inductive invariant for these examples. So I showed you the Lagrangians for Seeger and for ice learning, and it kind of lets you draw an interesting comparison between them based on which side do you have the lattice structure that ensures progress. So Seeger makes progress by accumulating predicates on the proof side, and ice learning makes progress by accumulating positive, negative, and transition counterexamples on the counterexample side. We also have a Lagrangian for Primal-Dual Houdini, which is fully symmetric, and it's a little bit interesting. It has 3 values, and the proof that it's well defined is a little tricky. We also have Lagrangians for termination with disjunctive rankings, and I don't know, Andreas, if you ever thought of it like this, but from this perspective, you see that the disjunctive rankings are a way to make progress and accumulate knowledge on the proof side for termination, because it lets you just accumulate the ranking functions and use a set of ranking functions. All right. So I think this framework kind of opens a lot of future directions and questions. One natural question is to add more algorithms. We have some Lagrangians in the paper, but I think there is room to extend it more. There is also room to extend our abstract algorithm because it's a very straightforward kind of 2-player game. It doesn't have some form of backtracking or recursion, and many verification algorithms have those. So it would be interesting to extend it. And I would like to encourage you to maybe think if your algorithm can fit this framework, and if yes, it's great, and if no, it's also great, because maybe we can extend the framework. Better understanding of the complexity is also a very interesting point. Maybe I won't go into it so much. And another point that's related to things that I really learned from Ken is the connection from relaxation. So Ken, you're not a co-author of this work, but I think you see the reflections of many talks that we've had in this work. And I guess before I fully understood it, you tried to teach me that if you think of Seeger or ice learning, on each of them you relax on a different side. And this framework kind of shows you which side makes progress. I'm not sure if it really captures this notion of relaxation, or maybe there is something we're still missing here. I think there is also room to better understand the connection with abstract interpretation, and of course apply to more domains. All right, so let me conclude. So we talked a little bit about induction duality and this kind of symmetric Primal-Dual algorithm, and if anyone is interested, I'm happy to talk about it more. We also talked about this Lagrangian duality that formalizes duality in many more verification algorithms, and has many future directions, and maybe you can apply it to domains or algorithms that you care about. And I hope you've seen that really a lot of this, some of it I did with Ken, but even the things that I didn't do with Ken, really Ken is reflected a lot in the app, and has impacted them a lot. And really I want to take this opportunity to thank you, Ken, for all of the impact you've had on me since the beginning of my journey in research, up until now. Thank you. And thank you all for.
Yes.
It's a beautifully elegant framework, but I'll ask the question which I can ask you.
I was going to ask.
Does it
Exactly the same.
Does it lead to better computational results?
Yes, that's a very valid question. So I think so in the Popple 25 paper, we have a new algorithm for fixed point logic.
You had fixed point logic on your own slide.
Yeah.
So you had fixed point logic. You won't quantify.
You're right. No, but I guess that I'll tell you, just because you gave me the opportunity, I'll tell you a little bit more about that. Let me go to this. So here, there is a Lagrangian for termination. And here there is a Lagrangian for an existing algorithm just for first order logic with quantifiers. Okay? And this new algorithm kind of combines the ideas it uses. So you can think of quantification plus fixed point. You need something to handle the quantifiers, and you need something to handle the fixed point, which is kind of similar to termination. And the algorithm that we get is just by combining ideas from these two algorithms. And you know, if you want to kind of be to make my life hard, you can ask me, well, couldn't have you thought about this combination without all this Lagrangian framework?
No, that's not
And
fair question.
is that-
No, I'm not asking that question.
Well, anyway, I'm going to answer that yes, but I still think that formalizing different algorithms
Okay, so you're
in
saying,
uniform ways lets you think about new algorithms. And we have one example, and since then there is another example that we're working on.
We can be late to the coffee break, that's.
So, but I want to ask for IC3, so making progress in proofs or in counterexamples? It's a trick question.
It's on proofs.
But IC3 actually has an inner loop and an outer loop, right? So the inner loop is predicate abstraction, right? It's adding clauses, right? So that's essentially making progress in the space of proofs.
Yeah.
But the outer loop is increasing K. And as you increase K, you increase the space of counterexamples. Right?
Well, you increase the space of counterexamples, but you don't accumulate the counterexamples you've seen so far. You don't. Well, if you preserve the proof goals, and you, well, you can think more about that. But I would say
I'd be
simple
interested to
answer
see
would
what
be
the Lagrangian formulation of IC3 would be.
yeah. So that's one of
Really do it.
one of my items for my agenda for CAV is to talk to you more about that. So that's
Okay, lovely.
All right, thank you, Oded.
Thank you.